Topic we'll be discussing in this lecture is dynamic source routing, and also we'll be discussing one more routing technique which is called as routing using alternative metrics. So first let us start with dynamic source routing algorithm. Previously we have discussed briefly about DSDV, destination sequence distance vector routing algorithm. The problem with the destination sequence distance vector routing algorithm is it the algorithm requires that the routing table should be updated every time, even when there is a small change in the network. Okay, so even if the data transmission in the network is very low, or if the network is slightly loaded also, the routing table will be keep on getting updated. Because of that, there will be always some uh, transmission of information will be happening. And so that what happens in the sense, even though there is no data or very less data to be transmitted, but the network is always busy with updating the routing tables, and hence the mobile nodes also may not be able to save their battery power. Considering all these issues, to avoid the unnecessary transfer of information for updating the routing table, uh, for even slight changes, or 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 transmission of, or to avoid transmission of unnecessary content, even when the network is lightly loaded. To avoid such things, we are going for the next routing algorithm, which is called as dynamic source routing algorithm. So this particular algorithm, it divides the entire task into two parts. It divides the task of routing into two separate problems. One is the route discovery problem, the other one is the route maintenance problem. So it divides the task of routing into two separate problems. These are route discovery and route maintenance. So with route discovery, what it does in the sense, a node will only try to discover a route. A node will only try to discover a route if it has something to send to the destination. Only when it want to send some information to the destination, and also only when currently there is no known route for that particular destination. Under this condition only, a node will try to discover a route. A node will try to discover a route only only when it want to send something to the destination, and only when there is no route to the that particular there is no known route to that particular destination. Under these two circumstances only, a node will try to discover a route. Similarly, the next task that it will do is route maintenance. So what is route maintenance? Assume a particular node is continuously using one particular path for data transmission. It is one particular path, it is keep on using for data transmission. Then it should ensure that that route is a correct route. That route is a correct route. That is, it is not broken in between, or initially it was good, or later it got broken. It should ensure that no such issues are there. Okay. As soon as the node detects any problem with that particular route, it has to find an alternative. Okay. So these are the so this is how DSR basically works at the top level. It divides the task of routing into two separate problems. One is route discovery, the other one is route maintenance. With route discovery, it tries to discover a route only when it want to send something, and only when there is no known route for that particular destination. With route maintenance, if a node is continuously using a same path, then the node should ensure that the path is perfect. If it finds something wrong with that path, then it should find an alternate path. Okay. Now let us see how. So let us discuss the algorithm of DSR, dynamic source routing algorithm. What it works, how it works. If a node needs to discover a route, that is, if a node wants to send some information to some particular node, destination node, and there is no known path for that destination, then it should perform route discovery. Then obviously it should perform route discovery. So under that situation, that is, if a node needs to discover a route, then it will broadcast a route request. Broadcast means it will send the message to everyone whoever is reachable. It will broadcast a route request with a unique identifier. It will broadcast a route request with a unique identifier and the destination address as the parameter. So in the route request message, the destination address will be the parameter. Okay. So any node that receives the route request will perform the following. Any node, so the first thing is, if a node wants to discover a route, it will broadcast a message with a unique identifier with the destination address, IP address. Okay. So as it is a broadcast message, many nodes will receive this message. So if any node receives this message, then what they should do in the sense, they should do any one of the following. If the node has already received this request, it should drop this packet. That's it. Because as it is a broadcast packet, the packet can come through different path. So maybe already this same request might have reached this particular node, and it might have already done what it is supposed to do. So if this is a duplicate packet that it is receiving, then it should drop that. So how to identify whether it is a duplicate packet or not? That is identified by the unique identifier. Okay, if it is receiving the same request with the same identifier, then it means that it's a duplicate packet. So it just discards it. This is the first option that will be done. The second is, if the node recognizes that this is the destination, the current node itself is the destination node, then it means that the request has already reached the target. If the node recognizes that, the current node itself is the destination node, the node recognizes that the current node itself is the destination node, it means that the data has already reached the request has already, not data, the request has already reached the target. So this is the destination node. So it means the job is done. Okay. So that's the second option. Otherwise, so if case 1 and case 2 is not satisfied, that is, if the node has not already received the request, or if this node is not the destination node, then what it will do in the sense, then it will append its own address to the list of paths or to the list of traversed hops in the packet and broadcast this updated route request. Okay. If 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 the request is not already received, and also if this is not the destination node, then it will just, then this node will take the packet and it will just broadcast it. But before broadcasting, it will add the address of this node also in the list of traversed hops. Okay. So originally in the list of traversed hops, only the source node will be there. Now when it goes to the next node also will be added, right? So this is how DSR algorithm works. Okay. So these are the 3 steps which are involved in the dynamic source routing algorithm. Now let us discuss this with an example. Consider this right side diagram. Let us assume that at this point of time, this is how the network looks like. Okay, this is the diagram which we already discussed. So I think no explanation is required. So this dark link represents good link and the lighter one represents weak link. Okay. So now let us see how a path can be identified from N1 to now how a path can be identified from N1 to N3. Let us see how to identify a path from N1 to N3 using DSR. using DSR, we want to identify the path from N1 to N3. Okay. So let us just apply that algorithm, the previous algorithm, whatever we have discussed. So N1 will send a root discovery packet. N1 will send a root discovery packet. It will broadcast a root discovery packet with the destination addresses N3. With the destination addresses N3. Okay. And also it will provide a unique identifier for this particular packet. So let us assume the unique identifier it gave is 42. The unique identifier is 42. So with this ID, it broadcasts this packet. So who will receive this packet? N2 will receive, and also N4 will receive this packet. Okay. Now go through the algorithm. What's the first step? If the node has already received the packet, then discard this. Okay, it will just drop the packet. So here let us check, is the node has already received this? N2 has already received this same packet 42, or N4 has received? No, they have not received. So they will accept it. So then the second step, it says, if this particular node itself is the destination node, then that's it. You need not do anything because this is a destination in case of N2. Or in case of N4, if this is the destination node, then also it means that the request has reached the target. Now in this case, this is not the destination node. So this is also not the destination node, and this is also not the duplicate packet. Now what N2 should do? N2 again, otherwise what it should do, the third step in the algorithm is, the second step is, if this node is the destination, then it has reached the target. Otherwise, the node appends its own address to the list of traversed hops and broadcasts this updated route request. Okay, so that is what it will do. So N2 will again broadcast. So if N2 broadcast, who will reach? It will to whom it will reach? It will reach to N5 and N3. It won't go to N4 because N4, N2 to N4 there is no path. Okay. So but now the packet will be, how it will transmit? The packet will be something like this now. When the packet reaches N3, it will be something like this. Okay. The destination is N3. The destination is N3, and the path traversed is N1 and N2. So it has reached so it should reach N3. It is supposed to reach N3, and so far the path traversed is N1 and N2, and the packet number is 42. Okay. So this is how the packet will look like. Similarly, the same packet will go to N4 also. Okay. Similarly, the same packet will go to N4 also, right? Okay. Now N4 also, sorry, similarly the same packet will go to N5 also. N5 also. Okay. Now N4 also should broadcast. N4, where it will broadcast? It will broadcast to N5, it will broadcast to N2, and also it will broadcast to N1. So how N4 will broadcast? The N4's packet will look something, the packet that N4 broadcast will look like this. The ID is 42. Okay, the ID of the packet is 42. The path traversed is N1 and N4. The path traversed is N1 and N4, and the destination is, in this case, the destination is always the destination is N3 only. Okay, the destination is N3. So this packet will go to N5. This packet will go to N1. Okay, it will go to N1. Also, this packet will go to N2. Okay, so I think it is clear. So there are two packets gone from N2. One is to N5, the other one is to N3, and this is the packet. And there are three packets gone from N4. These are to N1, N2, and N5. Okay. Now let us see one by one case what happens. Okay. So when the packet reaches N3 from N2, so N3 will know this is the target. Okay. So again, N3 will just you follow the algorithm. First, it will check whether it's a duplicate packet. N3 will check. No, it's not a duplicate packet. Is this is the destination? Yes, this is the destination. So the packet has reached the target. That's it, done. So it will stop here. But when the packet from N2 goes to N5, N5 also check the same thing. Is this is the is it a duplicate packet? That means does the node has received already a packet with the same ID? No, it has not received. This is the first time it is receiving from N2. Is this is the destination? No, this is not the destination. Then N5 should broadcast. N5 should broadcast. Okay, okay. But what N5 will broadcast, we will come to that later. But before that, let us finish the N4 cases. So N4 has broadcast this packet to N1, N2, and N5. Okay, so first it goes to N1. So N1 checks whether this is a duplicate packet. Yes, it is a duplicate packet because already N1 only originated this packet with the same ID 42. So N1 will just drop this packet. So it is dropped from N1. Okay. Then the packet also reached N2. So N2 check whether it's a duplicate packet. Yes, it's a duplicate packet. Already it has received that from N1. So N2 will drop. Then it goes to N5. N5 will check whether it's a duplicate packet. The packet from N4 also goes to N5. So N5 checks whether it's a duplicate packet. Yes, it's a duplicate packet because just before it has received from N2. So let us assume N2 from N5 from N5 has received the packet from N2 earlier than from N4. Okay, that I mean that the packet N5 has received N2's packet first, and then it is receiving N4. So obviously it will discard N4. Okay, so whatever the packets, so N4, so all the packets that were sent by N4 was dropped. Okay, all the packets that were sent to N4, all the packets that were sent by N4 were dropped. Okay, now let us see what N5 will do. N5 has got a packet from N2. Okay, so that is not a duplicate packet. So first step is not satisfied. Second is N5 is not the destination node. So N5 should broadcast that packet. To whom it will broadcast? It will broadcast only to N3 and N4. It will broadcast only to N3 and N4. Okay. So what it will broadcast? So it will broadcast something like this. The ID is 42. The ID of the packet is 42 and the path it has traversed is N1, N2, N5, N1, N2, N5 and the destination is N3. So this packet it will broadcast to, so this packet it will broadcast to N3 and also it will broadcast this to N4. Okay. Now when this packet reaches N4, N4 will check whether it's a duplicate packet. Yes, it's a duplicate packet. Already it has received a packet with 42 from N1. So, so N4 will just drop this. N3 will check whether it's N3 will check whether it's a duplicate packet. It's a duplicate packet, but still N3 is the destination. N3 is the destination. So N3 will accept this packet, but N3 has already received another packet. Okay, so N3 basically identified two paths. So there are two paths to reach N3 from N1, N1, N2, N3 and N1, N2, N5 and N3. So out of these two paths, this path is of shorter hop than this path. Okay. So finally, N3 will take this path and it will discard this path. Okay. So N3 now has this is the return path, N1, N2, N3. Okay. So this is how the dynamic source routing algorithm works. So now the return path also can follow the same thing. Okay. But this is applicable only in case of symmetric links. So N3 to also you can follow this, but this is applicable only in case of symmetric links. If it is asymmetric link, this way it won't work. Then the path from N1 to N3 is okay. Then N3 should identify its own path. Then N3 should if N3 want to reach N1, then again it should broadcast. Like how N1 does, like that N3 should broadcast. Okay, this diagram is basically for asymmetric links. Okay, so this whatever the algorithm we have discussed, it will only find the path from N1 to N3. Okay, If it is symmetric links, then the same can be used for the reverse path also. If it is asymmetric, then N3 also should again run the algorithm. N3 also should again broadcast that I want to find a path to N1. Like that it will broadcast. Okay. And initially it is starting with only N3. It is starting with only N3 and it may give some ID. So this time maybe the ID is 43. Right? This will go to N7 and N5. It won't go to N2 because there is no path. Okay. So again the algorithm will continue. Now N5 will check whether this is a duplicate packet. No. If this is the destination, no. So again it will broadcast. It will broadcast the same packet 43, but to the path it will add N5 also. N3, N5 and N1. It will add sorry, yeah, N1 is the destination. Okay. So all this information it will add to the packet and it will broadcast. So from N5 again it will broadcast to N3 and also to N4. When it goes to N3, N3 will discard because it's a duplicate packet. Okay. N4 will again broadcast to N2 and N1. So like that the path will be identified, right? So I think it's clear. You can work out on this. So this is the working principle of dynamic source routing algorithm. Here is another example which shows graphically how the dynamic source routing algorithm works. So consider this graph as a network of ad hoc nodes. Say we want to identify the path from C to O. You say the node C want to discover the path to O. So the route discovery, how it will send. First C will, here we consider all links as symmetric links. Here we consider the links as symmetric links. First C will broadcast. The broadcast will be received by B, E and G. Okay. So it goes to C, E and G. And the path is what? The destination is O. Starting from C, this is the ID. Destination is O. Started from C, this is the ID. Okay. Now G, E, B, E and B will check whether they are the whether it's a duplicate packet or not. No. Are they are the destination? No. So again they will broadcast. So when they broadcast, it is like this. When B broadcast, it is like this. Destination is O. The path traveled so far is C and B. And B will broadcast to A and D. Okay. When E broadcast, it will be like this. Destination is O. Path traversed is C and E. And this is the ID. And E will broadcast like this. Destination is O. Path traversed is C and G. And this is the ID. Okay. Like this, it continues. So when D broadcast, it will be like this. Destination is O, path traversed is C, B and D, and this is the ID. Or there are two paths available, or the alternate path is C, E, D, C, E and D, and this is the ID. Destination is O. Okay, and H will broadcast like this. Destination is O, path traversed is C, E, H. I will do like this. Destination is O, path traveled is C, G and I. Okay. Now, when the packet reaches K and J will broadcast like this. J will broadcast the destination is O, path traversed is C, E, H, J and ID. K will broadcast like this. Destination is O, path traversed is C, G, I and K and this is the ID. So whatever K sends, that will go to L and M. Whatever J sends, that will go to L and F. Okay. Now M broadcast something like this. Destination is O, path traversed is C, G, I, K, M. Okay. L traverse like this. Destination is O, path traversed is C, E, H, J, L, and this is the ID. For reaching L, there are two paths. Okay. One is C, E, H, L, J. That is this path C, E, H, L, J, and the other is C, G, I, K, L. Okay. This is another path C, G, I, K, L. Okay, so it provides two paths, alternate path, CGIKL. Okay. Finally, M will send to O and L will send to N. Okay. So finally, first L to N is something like this, CEHJL N, and M to O is like this, M. Uh, I mean the path is GIK GIK. Okay, that is not coming here. The path is CGIKM. Okay, CGIKM, and the reverse path is MKIG. This is the reverse path, MKIG, assuming it is a symmetric link. Okay. So this is how the dynamic source routing algorithm works. Now let us discuss another algorithm, which is using some other metrics. So this algorithm, in generic terms, it is called as alternative metrics. In generic term, it is called as alternative metrics, and specifically, this algorithm is called as least interference routing. Specifically, this algorithm is called as least interference routing. Typically, any routing algorithm will consider number of hops as the metric. That is, to identify the route, the best route, it will decide the number of hop as the metric. It will always try to identify the route with the least number of hops. The route with the least number of hop. Okay. Hop is this. S1 to, say for example, S1 to N3 is one hop, N3 to N2 is another hop, N2 is R1 is another hop. Okay. So if you are trying to find a path from S2 to R1, then this path S1 to N3, N3 to N2, N2 to R1, there are three hops. This is hop 1, this is hop 2, and this is hop 3. Okay. So a typical routing algorithm will work based on number of hops, and it will always try to minimize the number of paths. Okay, number of hops. But this number of hops may not be a best metric in case of ad hoc routing. This number of hops may not be a best metric in case of ad hoc routing. So here in this algorithm, we are considering interference as the hop. So we want to identify a route with least interference. We want to identify a route with least interference. Okay. So let us see how this algorithm works. And this is the graph we are considering. These are the various nodes. Okay, these are the various nodes. We want to find a path from S1 to R1 and also S2 to R2, and we want to identify a least interference path. We want to identify a path from S1 to R1 and S2 to R2, and that path should be a least interference path. Okay. First, let us identify path based on hops. From S1 to R1, let us identify a path based on hop. So there are two paths available. One is this is the path 1, S1 to N3, N3 to N4, and N4 to R1. So this has three hops, 1, 2, and 3. Similarly, there is another path, S1 to N3, N3 to N2, and N2 to R1. This is another path, S1 to N3, N3 to N2, and N2 to R1. This is another path. Okay. Both this path has only three hops. Okay. There is no other path which is less than three hops. Okay. So if you use hop based routing, then any one of these path will be considered as the best path. Similarly, if you take S2 to R2, this will be treated as the best path with hop based routing, S2 to N5, N5 to N6, and N6 to R2. Okay. Again, this has three hops, S2 to N5, N5 to N6, N6 to R2, three hops. So there is no other path from S2 to R2 with less than three hops. So if you take hop as the metric, then again this will be considered as the best path. But let us see how to find a route using least interference routing technique. So this is the scenario. S1 wants to send a packet to R1 and S2 want to send a packet to R2. Using hop as a metric, S1 could choose three different paths. These are the different paths available from S1. Either it can choose N3, N4, R1, or N3, N2, R1, or N1, N2, R1. Okay, there are three paths. I left out one path. So I told two. The another one is this path is also three hops only. S1 to N1, N1 to N2, and N2 to R1. So these are the three paths available from S1 to R1 with hop based routing. Okay. Similarly, from S2 to R2, there is only one path. That is, there is only one path, and that path is this. Whatever we have discussed previously, it is S2 to N5, N5 to N6, and N5 to R2. Okay. So that is the path we have from uh, S2 to R2. Okay. Not coming, but that is the path, right? Now let us see how the least inference routing work. Least interference routing works. So if you refer that particular graph, interference of node 3 is 6. Interference of node 4 is 5. How we got this value? How we got this value? How we say that interference of node 3 is 6? How we got this value in the sense? Just you see, node 3 can overhear whose communication? Node 3 can overhear the communication of S1. It can overhear the communication of N5. It can overhear the communication of N6. It can overhear the communication of N2. Also, it can overhear the communication of N1. So how many communication it can overhear? Just number 1, 2, 3, 4, 5. Okay. So totally 1, 2, 3, 4, 5, 6. It can overhear N4 also. Okay. So totally it can overhear 6 communications. So its interference value is 6. So its interference value is 6. Right? That is how we got 6. Similarly, if you see N4, how many communication it can overhear? It can overhear N6, it can overhear N3, it can overhear N2, okay? It can overhear R1, it can overhear R2. So its interference value will be 5. 1, 2, 3, 4, 5. So like this, we calculate the interference value for any node. Okay? Like this, you can calculate the interference value for any node. Now, now let us calculate, based on this interference value, let us calculate the cost of possible path between S1 to R1. So in the previous slide, we identified three possible paths from S1 to R1 based on least hop. So these are the three possible paths. For all these paths, let us identify the cost in terms of interference. Let us identify the cost in terms of interference. Okay. So how to identify in the sense? So the cost from the first cost value is 16. Let us see, take only one. The first cost value is 16. It is S1 to N3, N3 to N4, N4 to R1. How it is 16? Let us see. S1 to N3, N3 to N4, N4 to R1. Okay, so we are discussing this particular path. Let me delete all other things. We are discussing this particular path. S1 to N3, N3 to N4, N4 to R1. So this particular path, what is the cost? So for all these nodes, calculate the interference value and add it. That is the cost. For all these nodes, calculate the interference value and add it. So what is the interference value of S1? S1 can overhear S2, N3 and N1. So it is 3. N3 interference already we have calculated. It is 6. 1, 2, 3, 4, 5, 6. Its interference value is 6. N4, it is 1, 2, 3, 4, 5. Okay. It's 5. Okay. R1, it is 1 and 2. Okay. So if you just add all these things, what you get is 6 plus 3, 9. 9 plus 5, 14. 14 plus 2 is 16. That is the cost of this particular path. That is the cost of the path from S1 to N3, N3 to N4, N4 to R1. Similarly, calculate the cost from S1 to N3, N3 to N2, N2 to R1. Similarly, calculate the path from S1 to N3 and N3 to N2, and N2 to R1. Okay, so now we are taking this path S1 to N3, N3 to N2, and N2 to R1. So now calculate the interference value for all. So this already we know 3, this already we know 6. So the interference value for this is 1, 2, 3, 4. Okay. The interference value for this is 1 and 2. Okay. So if you sum up all these things, 6 plus 3, 9, 9 plus 4, 13, 13 plus 2, 15. So this is the cost of the second path. This is the cost of the second path. Okay. Similarly, calculate the cost of the third path. S1 to N1, N1 to N2, N2 to R1. So the third path, that is S1 to N1, N1 to N2, and N2 to R1. So again calculate the interference value for all the nodes. S1 interference value is 3. N1 interference value is 1, 2, 3. This is also 3. Okay, because it can over here only 3. N2's interference value is 1, 2, 3, 4. Okay. R1's interference value is 1 and 2. So just add this 3 plus 3, 6, 6 plus 4, 10, 10 plus 2, 12. Okay. So the cost of the third path is 12. Okay. So out of the 3 possible paths, now you take the one with the least cost. So the one with the least cost is this. The one with the least cost is this particular path. Okay. So hence this is the path with the least interference. Hence this is the path with least interference. So this path is preferred for ad hoc routing. Okay. Similarly, we can work out for what you call. Similarly, we can work out for S2 to R2 also. So if you take S2 to R2, we identified first only one path, which is N5, N6, and N2, R2, N5, N6, and R2. So if you go there, if you take this path N5, N6, and R2, calculate the cost, calculate the interference value for all the nodes involved. So the interference value for S2 is 1, 2, and 3. For N5 is 1, 2, 3, 4. Okay. For N6 is 1, 2, 3, 4, 5, 6. For R2 is 1, 2, 3. Okay. So you just add all these things. 4 plus 3, 7. 7 plus 6, 13. 13 plus 3, 16. This is the cost of this particular path. Right. So the cost of that particular path is 16. Okay. But let us here there is only one path with the least hop. This is the least hop path. But let us try to identify if there is any other path which will give a least interference even if the hop count is more. So let us explore another path. Let us explore another path which is S2 to N7, N7 to N8, N8 to N9, and N9 to R2. So this has 4 hops. 1, 2, 3, 4. Even though it has 4 hops, let us see what is its cost. So this path, let us take this path and identify the cost of this particular path. Okay, so the interference value for S2 is 3. For N7 is 1, 2, 3. This is also 3. For N4, for N8 is 1, 2, 3. This is also 3. For N9, it is 1, 2, 3. This is also 3. And for R2 is 1, 2, 3. Okay. So if you add all these things, 3 plus 3, 6, 9, 12, 15. So actually this gives a less interference than the previous path. This gives a less interference than the previous path. Okay, so so what happens here is, even though this path having a longer hop, but with respect to least interference, this is better. So S2 to R2, we will go with this particular cost path. Okay, so this is how the least interference routing algorithm works, right? So like this, there can be several metrics can be applied. The routing algorithm need not work on hop or interferences. There may be several metrics which are available that can be included, or multiple metrics can be combined. For example, you can include hops, you can you include interference, you can include reliability, you can include error rate, etc. And then you can find the cost. And then you can find the cost something like alpha cost equal to alpha h plus beta I plus lambda r plus delta e plus any other parameters also. So in this case, we have to identify the correct value for alpha, beta, gamma, and delta. That is, these are the weights. But identifying these weights are not that easy. Even we can use some machine learning techniques to identify the best weights to reduce the cost. Right? So that's it about interference routing algorithm. So we have discussed two routing algorithms here: dynamic source routing algorithm and interference, least interference routing algorithm. Okay, fine. Let us stop here. Thank you.